Recording. Okay. So we want to visualize how the surface water is changing over time and quantify those changes. And just a introduction, like surface water is any body that of water found on the earth's surface, and it also includes the water body in like salt water in the ocean and fresh waters in river or streams. So today's case study is on the surface water on land, which is in the border of Afghanistan, and this lake was disappeared recently, I think after 2000, and we are going to do a case study on it. So the method that we are going to use today is we will identify the suitable data sources. So based on our requirement, which data source might be more suitable. So we'll do that. And next step is image pre-processing, because there will be some issues when we just import the data set into our any processing libraries. So we have to do some pre-processing step to eliminate those issues. So that's why we'll do some pre-processing step, and the main task we are going to do is cloud masking. So when we are working with the optical imagery, then the presence of cloud is a big issue, and so we want to remove those abnormalities caused by clouds. And the third step is water body extraction. So there are several methods that we can employ to extract the water body. So today in this session we are going to apply the indices based water detection technique. So basically we'll calculate some of the indices like NDVI, NDWI, and we will apply some mathematical operation over mathematical logic over them, and hence derive the water body. But there are other other water extraction algorithms and techniques as well that I'll explain in the slide. But out of 3 or 4 we will apply 2 of those techniques. And also we are going to visualize a long-term change in the water body. So what we are going to do is we are going to derive an annual I think every 5 years. So every 5 year we are going to see the change in the surface water. The second last step is post processing. So we'll use some filters to remove not remote, isolated pixels. So when we try to detect the water, there will be some noise around the water bodies. So those small isolated pixels are not truly representing the water, but simply just noise. So we try to eliminate those pixels, and the final operation is raster to vector. So if we are working with the raster operation, all the input and output are rasters. So we want to convert that to a vector data type like SAFE files. So we can also work on our GIS application. And the last step is of course data visualization, and we will plot the surface water change and to understand the trend. Yeah. And yeah, so to understand what are the categories of or techniques for surface water extraction, so these 3 are the most commonly used techniques. So first one is single band based method. So as we saw yesterday, there were almost 19 bands in Landsat imagery. So in Landsat 7 or 8, I think 8, yeah. So if we just take a single band from that and calculate some and derive some threshold, then we can also derive water body if we can properly identify a threshold. So that is a single band based method. So it does not require any complex logic to process, but it will just take a single band and simple mathematical operation. So the second step is spectral index based method. So in this method we are going to calculate complex indices like vegetation indices like NDVI, NDWI and all those, and we are trying to apply some logic over that and then derive the surface water. This has a added advantage of over using the single band based method. So because we are going to do both first and second today, we can also compare the result how they will vary. And in the third step there is also a machine learning and deep learning based method. Basically in the machine learning based method we try to train a regression model or a classification model like yeah. So yeah, when we train those models we need to give them some input so that the model can learn that this is the water body, and then we use that trained model to do the predictions. So this is also getting more more research nowadays, and but for today we will not go through this because we have to prepare a training data set and again train the model, which will take a long time. But in the tomorrow session, you will learn some machine learning based method for land use classification, and in that session, I think you will be able to replicate that process for water delineation also. Yeah. To explain more on single band based method, we just make use of a single band for detection, as I mentioned earlier, and the most suitable in optical based observation is that we use near infrared region of the electromagnetic spectrum. So instead of red, green, or blue, if we use NIR region, then it is very it is proven to be one of the best band for water detection, because the reason is that the radiation within the NIR region is absorbed almost completely by the water. So we can just apply some threshold, because the in NIR image water will appear completely dark, and hence by applying some certain threshold we can get the water body. And yeah, the last also explains the same. We use thresholding on a digital number or the pixel. So the categories are intensity thresholding. So because the raster image has a digital number, that we use that intensity information to do thresholding. But there is also a second category of thresholding, which is known as histogram based thresholding. So this histogram based thresholding I will explain in the next coming slide. And the major issue with working with a single band based method is that it can sometimes the shadows of mountain or cloud can also cause error in our water detection, because we are completely relying. Yeah, sure. Like you can find the presentation link in the chat. So this is the same slide we used yesterday. I've just added the content below that. Okay, so yeah, the main problem is here shadows of mountain or cloud. And so this is all about single band based method. If you have any queries, please feel free to unmute, or yeah, you can also drop the question in chat. Okay, so as I mentioned earlier, there is two techniques here: intensity thresholding and histogram thresholding. So yesterday also we did one thresholding on DEM. So that is the intensity thresholding, because we are just looking into the digital number value on the satellite image, right? But in the second part, this histogram based thresholding, what we do is we try to plot the frequency with the backscattering intensity. And this is the example of a Sentinel-1 or type of data, which is the SAR dataset. It is a radar imagery. So normally whenever there is a water surface, then the distribution will be bimodal. So it uses some statistical technique to derive a threshold. So this threshold is derived, and below this threshold it can be marked as water, and above this threshold it will be marked as non-water or any other feature on the earth surface. So this is the basic concept of histogram based thresholding, and today we are going to look more into this, but sorry, not this, the intensity based thresholding. This Otsu-built thresholding is applying some mathematical concepts. So it has some complicated algorithms. We are using this technique in flood mapping applications in GIC itself, but yeah, today we'll skip this part. So the other one is spectral index based method. This will have an improvement over the single band based method we discussed earlier. And the concept is that we can use band ratios, and it can normalize the effect of some unwanted information in pixels, like clouds and shadows. So this can eliminate some of the issues present in the single band based method. And there are several techniques nowadays which has been proposed to for utilizing complex ratios of multiple bands to derive the surface water. And most commonly used spectral band are NDVI, EVI, NDWI, EWI, and MNDWI. So some of them we already calculated yesterday, and some of them we will do it today. And in the last, we use machine learning based methods. So there are some regression and classification algorithm. And regression, when you train the regression algorithm, it just tries to predict the output value based on the input that we gave, right? But the classification algorithm will try to group the input value into different classes. So it might fall into the water, or it might fall into other classes, that kind of classification. And the classification algorithm is either supervised or unsupervised. And In the supervised part, we have artificial neural network, SVM, and maximum likelihood classification. These are some commonly used supervised algorithms. And for unsupervised, we can this k-means clustering and isodata clustering are most common. They are also available in ArcGIS environment. Yeah, so this is basic example of the deep learning based implementation, where we take the input, and also we have the labels, like for machine to understand that this is the water boundary that we want to detect, and we train the classifier or the algorithm, and in the output will give you the result will be the output, which will give you based on the training data set. So the quality of the output is dependent upon the quality of your input. Yeah, so more or less this is like a black box where you train the model, and it will give you an output, but you will not know much detail what is going on inside this. So these are some of the techniques. Yeah, as I mentioned earlier, we'll use single band and spectral index based method. So if you go to the Google Drive now, yeah, sorry, if you have any queries, please feel free with by unmuting or on chat. Okay. Yeah, so if you go to this website, I'll drop in the chat for Google Drive. Yeah, so there is this day 2 folder where you can find all the notebook that we are going to use. So you can simply click on open with and Google Colab. Yeah, when you go to day 2, this first notebook called day 2 surface water dynamics, right click on it and then open with Google Collaboratory.
Sorry, how can we access your this folder? Because I don't have it in my Google Drive. Is it I have to add it, or somebody has to share it?
Can you check this link that I said in chat? Yeah, can you access it? This URL.
Now got it. Thank you.
Okay. Yeah, it's inside day 2 and the first one. So let me know if you can access. You can give thumbs up in Zoom, or you can drop message in chat. Okay. Let's see. Right. So if you open it in Colab like this, then this notebook will open up. Yeah. Now we can start working. So what you have to do is you go to File and then you click Save or Copy in Drive. I think, or otherwise we are going to edit the same code.
Excuse me, Hassan.
Sorry?
There is no Google Collaborator in my PC, so how can we open with in Google Collaborator?
So in that case, you can go to collab.google, right? I'll drop this chat in this chat. Yeah. So after you go here, so go to new notebook. Right. This is a blank notebook. So now we are going to upload it here. So for that, you will have to download it first. Go to File. Sorry, not here, but
already downloaded.
Yeah. So if you have already downloaded it, then you can upload it from File and Upload Notebook.
Okay. Okay.
Yeah, you can browse to your PC from here.
So Google Collaborate is an application, right?
Yeah. We also used it yesterday. So it is for to run the Python-based code. So you can run your code here. Yeah. So instead, yesterday we did copy pasting, but I think that was inefficient. So you can just import the whole notebook, and you can also work on it at the same time.
So I mean, we can also download the collab.google as an app to our PC.
No, it only runs on the cloud. So it is a cloud-based application, similar like
Okay.
similar to a
Okay.
Google Earth Engine. Yeah.
Right.
Okay, so can you all access this notebook in this format? So if not,
Can I continue in my yesterday's notebook also?
I think no, because we are trying to import this whole code into the collab, so we have to
Okay.
import this whole code.
Okay.
Yeah.
Okay.
So the way is like you can, if you can access this Google Colab, then you can directly use Open with Google Colab. But if that option is not there, first you have to download it from here into your local PC, and then like in this process, you can go to File and then Upload Notebook, and then you can browse.
Browse the one in the Google Drive that you share.
Yeah. So for example, this one is already uploaded, right? So
Okay.
this you can open. Sorry, download it. So it has to be downloaded on your PC first. Can you let me know if everyone can access this or not? So after importing, you will be able to see this page. D2 surface water dynamics and these informations. Okay, I'll start from here, and if you cannot access this, just let me know. Okay, so first, this is as I discussed, we are trying to understand what kind of a sensor we want to use, because we want to go back in time around 1985. So it means the available high quality data is from Landsat 5, sorry, from the Landsat program. So these are the selection guide that I prepared for. There is some overlap for, let's say, if you come after 2000 also, there will be data from Landsat 5, but you already have a quality data from Landsat 7. That's why I have prepared this guide. So if you want to select a data for let's say 1985, go with Landsat 5, but from 1999 to 2013, you can go with Landsat 7, and so on. So this uses different kind of sensor based on this Landsat program. For 5, it uses multispectral sensor, and ETM in Landsat 7. Similarly, OLI TIRS sensor in Landsat 8, and the same sensor for Landsat 9 also. So this is the atmospheric transmission window, and this is the electromagnetic wave of different wavelength that will be transmitted from that can be transmitted towards the sensor from the surface of the Earth. So if you see, this multispectral sensor has only 4 band within this small narrow range of a wavelength. But if you go to thematic mapper, so in the thematic mapper you have these almost 6 band, and ETM plus you have almost 8 bands. And
excuse me, Elson.
Yeah.
Could you please elaborate a little bit more the introduction parts? So what are we doing with these today's sessions? I mean, the surface water dynamics.
Yeah. So this slide, you mean this slide, right?
No.
So what we are going to do today?
The work you are
basically
doing.
The purpose of what we will be doing today. Why we are doing this, and for what purpose, basically.
Yeah. So
yes.
Yeah, maybe I'll try to explain it here. So basically, there is a lake in Afghanistan, Gowd-e-Zareh, and this lake has completely disappeared in recent years. So we want to see how the lake has changed over years, and map the trend, like how much water has been changing over this over several decades. So we want to map the surface water dynamics, and for that we are using satellite time series satellite data to map these changes, to understand these changes. So if you have any queries, yeah, please let me know. So for that, let's say we want to go back around 1985. So so we do not have access to Sentinel-2 dataset of that time. So the best choice we have is a Landsat from the Landsat data. So we are mapping it from 1985 to 2020. So these are the Landsat data selection guide that we are going to use. And yeah, so we'll use Landsat 5, 7, and 8 for this study. And these are the band information. Like if you see here in the right, I mentioned that Landsat 5 has multispectral sensor. So to know what are the band that is in the multispectral sensor, this chart will help to understand. So for multispectral sensor, there is only 4 band, and this is the electromagnetic spectrum. Like a wavelength will be transmitted from sunlight to the earth, and that wavelength will be reflected back to the optical sensor, just like how our mobile phone camera works. So this multispectral sensor can only uh, read the information within this narrow range of bands. So I think it's RGB and NIR probably. And there are so when we go, the new quality of sensors has improved, increased more band. So it is so there are many number of band than the multispectral sensors. So we're just trying to understand this first. And then in the coming part we are going to study the how this lake has, the water in this lake has changed, and we try to quantify this and plot a chart and visualization on how surface water is changing over time. Yeah, so if you can access this notebook, you can drag and see that the surface water in this lake has completely disappeared between the time period 2000 and 2009. So yeah, we'll try to extract the water body and then see how the area is changing over the time. Yeah, if it's
Ilsan,
clear.
how did you select this water reservoir? I mean, through a GPS point or through Google Earth? How did you select this? How did you find it?
This site.
Mm-hmm.
Yeah, so this I just searched for in internet, like which lake has been recently disappeared in Afghanistan. So the one name that continuously came was this one, and there was other lake also. I forgot the name right now, but there are 2 lakes that that were rapidly disappeared, right? So that's why I chose this lake as a case study.
Okay.
Okay, yeah, if you can access this notebook, then you can also drag and see how the surface water had changed. Yeah, sure, sure. This GPS location I will share with you. So actually it is near this border area. Okay, around the bottom of Afghanistan. This is the area.
Okay, it's in the border with Iran, basically.
Yeah, yeah.
In Pakistan.
Yeah, around this
Okay,
corner.
this is Pakistan. Yeah, it's Pakistan, basically.
Yeah, I can share with you the coordinates, and you can see in Google Map
Okay.
also.
Thank you.
Yeah, this is the coordinate. So we'll begin the Google Earth Engine session from here. So in the first part, as we did yesterday, we'll import all the necessary libraries like NumPy, Matplotlib, and Pandas. So basically, if I forgot to give you some introduction yesterday, so this NumPy we used to read the image data as array. So this is also a Python based library, and it is very useful to read the image, the array based data set. So the second one, Matplotlib, is used for plotting and plotting the graphs, and in the later part also we'll plot the trend line. So that kind of plotting will be helped by Matplotlib. and pandas for organizing a data frame. So let's say if we have attribute data in if you have attribute data in vector data set like save file, then that attribute data can be read using the pandas library. Similarly, this IPy widget are to display this HTML page in this notebook. And this gmap library, as we discussed yesterday also, it is used for for the map visualization like these. So we can import map into our Jupyter notebook environment. So the next one is import EE, which is basically importing the auth engine library. And next step, we have to authenticate it, right? So after you perform this authorization, you will be able to access all the functions and dataset that is available within auth engine. So let's run it. So to run it, you can also press on this play button, or you can click on shift and enter. So just hold down shift and enter. So it will run, and then if the authentication is completed, it will show true. Yeah, and I'll also explain this second step for initialization. So as yesterday, if you have any issue with the initialization, you can follow this presentation slide that I have shared. But if not, if you remember your project name, you can simply replace this my project name with yours. Yeah, and if you replace this, it will run. But if you just take this as default, it will show error in your part. So let me know if you so if you want to know this this part, then just follow this presentation, or you can also see the yesterday's code in Colab. So there also you have already used your project ID. I'll drop this URL in chat. So if you are having any trouble finding your project ID, you can also find it from this website. Yeah, let me know if you can initialize this this part, this auth engine from this code. Yeah, can you give thumbs up if you have done it? Can anyone verify if this is completed or not?
What were we searching at that in there yesterday?
I see.
Sorry.
Okay, so
In APIs, after APIs, what we
you mean in this page or
no, in the previous one.
here? Just a moment. Yeah, if you go to your yesterday's notebook also, you can see this is in different. Yeah, in your yesterday's notebook, you can find this ee.initialize and then project ID here.
We enabled it. Then what will happen?
Actually, you don't have to enable it. If you have worked on it yesterday, you can use the same project ID today also. So to find that, you can go to collab.google and then open yesterday's notebook. Open notebook, and then here you can find recap of Google GEE. You can open the yesterday's notebook and you can find it there. I think that will be the easier way. But the other option is you can go to this Google Cloud Console, that the URL I have sent in chat, and then you can select the project from here. And after selecting, your project ID will be in this page. You can also copy from here.
Copied it, but we have to paste it now.
Yeah, so after that, it has to be on a single quote. So after project
Okay.
equals to and single quote, and you have to keep it inside this quote.
Okay. So for me, it gives error. I don't know.
So is it the same error like yesterday, or you can share your screen and you can fix that?
Initialization completed.
Yeah, so the initialization, there is no error, right?
No, for me, no. I just put my project ID and then
Okay, yeah, it should work. Yeah, so sometimes sometimes the yeah, sorry. Yeah, in some cases the issue is that the APIs or services are not activated. So if that is your case, then let me know. Then we can fix that by yeah, we can fix that by sharing the screen. Yeah.
So here's
Yeah,
one more question.
yes.
When we set up our Google Earth Engine project,
Mhm.
we got a specific number for the project ID.
Yes.
So we cannot create other IDs, or this project ID will always work, and we have to work in this project ID, or we
Mhm.
can create many projects. This is some
Actually,
basic question.
yeah. So the thing is, you can create many projects. So in my case, you can see there are three, but in my personal account, I think there are more projects. So when you create a new project, you can do it from this Cloud Console here. So if you go to Cloud Console, then you can create a new project. And previously, like in Earth Engine, you don't have to create any projects. Like just 3 or 4 days back, this is a recent change in Google side. So if you click on new project, it will give you some forms that you have to fill, and a new project will be created. And based on the name, your ID will be automatically created. So there you will have an option to set the ID. But if you do not give any ID, they will assign it itself. So this is randomly, right? So this is, but it does not matter because your project name will still be the one that you choose. And
So
after you create,
for the first time, Google Earth Engine you can create one ID, and for the next time you have to go to console.cloud to create new IDs.
yeah, so you have to create a new project, and that project will have an ID that you have to give it to this notebook. So once you do that, then you can always use that, reuse that ID. But if you
Okay.
forgot it, you can check it from this console itself, or you can create a new project. But even after you create a new project, sometimes the extension is not enabled, like the Earth Engine service is not enabled. So you have to go into this enable API and services inside that project. So it is available,
Okay.
I think, in the bottom here, API and services, and then
Could
yeah,
you please paste this console.cloud.google link
yeah,
in the
sure,
chat box?
yeah. So this all the step, if you find it confusing, then I have also provided a presentation slide. So there are 4 steps that you have to follow. Yeah, and yeah, I think this presentation will be sufficient to do the authentication.
Okay.
So but each individual will have a different project ID, so it will not match, and that's why it will create a conflict. So when you are using, trying to use the same project ID as mine.
So
Okay,
one
so
more
if
question. One more
yes,
question.
yeah.
So when a team is working on the same project,
Mm-hmm.
they cannot use from different PCs the same project. The same project cannot be used from the different PCs.
Same project cannot be no,
I mean,
the thing, yeah.
suppose
Mm-hmm.
the JIP team is working from Kabul and provincial offices,
I see,
and we are
yeah,
working on the same project. So we are apart from each other.
yeah.
So
So
we cannot access the same project from
yeah,
different users.
so the concept is this project belongs to my Gmail account, right?
Mm-hmm.
So if you have like a shared Gmail account, then you can log in to this collab also with the same Gmail account, and also to this cloud console with the same Gmail account, so that you can access that way. But the question that you asked, that a shared project will work or not, that I also have to explore, because this is a very recent change, less than a week. So I have to explore that one. Yeah.
Okay. Okay.
But I think it is possible, yeah, because in Google, like most of the thing you can easily share and work collaboratively, so I think it should be possible, yeah.
Mm-hmm. In this coding system is called algorithm.
So you mean this space?
Mm-hmm.
So this is called Colab. So it is basically a Jupyter notebook environment. So this means when you have a Python code, you can either run it in your PC like interpreter, or you can have this environment, this Jupyter notebook. So the this is more easier to use, and you run a code and you can see the output. So it is more convenient to run in this one. So anyone new to Python or Python programming, I would recommend using this this notebook environment, because you can write a single line of code and see the output, and then you can know like if you have done any wrong in the previous step. And also it's really easy for teaching and learning purpose. So that's why, yeah. So this is mainly for running the Python codes.
Okay.
Yeah. So is it done in your side?
Yeah, it's done on my side.
Okay, so let me know if it's not completed on your end. Otherwise, I'll move on to the next step. So this is the same as we did yesterday. We were trying to set up the map visualization parameter. So the Landsat value will range from 0 to 65,000. So any pixel can have values ranging between these two values. So if you give the whole range, then the image will not have a very contrast, but the image will look very bright in some case or dark in other cases. So we just want to limit the pixel value between this minimum and maximum range of 30,000, 0 and 30,000. So it will improve the contrast of the image. And the second part is the band combination. As we said yesterday, there is a true color composite, and several combination of band can also produce a false color composite. So in this case, we use band 3, band 2, and band 1 for Landsat 4, 5, and 7. So what this will do is this will create a true color composite image for Landsat 4, 5, 7. But the band combination is different for Landsat 8, where we will have to use 4, 3, and 2 instead of 3, 2, and 1. Right? So this information you can also find in the yesterday's notebook. I have shared a S3 link where you can find that all the band information, which band represents what. So typically we are trying to create a red, green, and blue combination. So here band 4 represents red in case of Landsat 8, 3 represents green, and band 2 represents blue. Yeah, in this order. And there is two visual parameter that I have created. This one is for the original Landsat image, but we are not going to work on the original Landsat image itself. So we are going to first normalize the data. So that means the value range is from 0 to 65,000, and when our algorithm performs some calculation, then it is difficult to do a calculation over very large number. So we want to limit our data value range from 0 to 1. So I mean, we perform some kind of a mathematical division operation or multiply it with very small number, so that the data set will be scaled. Okay, so this step is called scaling or data normalization step. Basically, whenever you are working with machine learning or some kind of algorithm, then it becomes really convenient to use the scale data set. And same is the case for this Landsat 8. We use the original image for visualization, but also we have the image for calculation, that is the scaled version. So all the data set will not range from 0 to 65,000, but it will range from between 0 to 1. And these are some map visualization parameters. So if we change anything here, then this map display will change. So let's say from 40 to 100%, if you change, this map will be will occupy 100% in your screen. And this is the map center. So in this whole globe, where you want to the map to be initialized. So I have so this is our study area. So I have put center around this area. So whenever you reload it, it will always come around this area. So that is the concept. And after you run this Landsat, this map visualization parameter code, it prompts you to select area of interest using draw a rectangle tool. So if you see in the left corner here, there is a rectangle tool. Yeah, approximately just there you can see some small water patches. Just draw a big box around it. Yeah, so this becomes our area of interest. So I try to make this code reusable, so that if you have any other study area, let's say this, you can easily just draw this rectangle around that water body, and your whole code will start working on that area, on that study area. So for now, we will take this AOI. So for comparison, because I know the for this case study, like the water has gone down. So yeah, so if we use the same, then our result might look very similar if we work over the same study area. So I suggest everyone to work on this area. Yeah. So there is this small water like patch. Yeah, you can create a rectangle over it using this tool. Yeah, and do not draw two rectangles, because it will create issue. So you can only select one area of interest in this code. Only after you complete this step, you can run this map draw control.data. We want to see what is the information that is stored in this area of interest. So can you see this geometry information when you try to print this data? If this geometry is working, then only you can move to the next step, because all our immediately next code will use this area of interest to do the calculation. So that's why we need this polygon or area of interest. So after initialization, you have to run this script where it will ask to draw a rectangle using rectangle tool. It's available here, and once you draw this, the next step will show you what geometry you have drawn. So So this is the coordinate of the geometry that we have drawn in this step. Let me zoom in a little bit. Yeah. So this other step, as you can see here, there are some other information. Yeah.
Hilson, it shows an error for me, maximum error or error margin optional. The draw control data contain detailed information and type. Okay.
Yeah.
So I have the coordinates, geometry coordinates.
So is there any issue now, or it's working fine?
I think it's working fine.
Okay.
Sorry.
It's fine. Yeah. So we are trying. So what we did here was we draw a polygon, but it is drawn in our Python code. So our Earth engine does not know what this polygon means. So we have to convert this data type to Earth engine data type. So it means Earth engine vector data type, right? So what we do, we grab this coordinate, this coordinate from this geometry information, and then we can use in our following codes. So here I said we get the coordinate data and convert into Earth engine geometry type, and this is the method to do that, ee.geometry.polygon. And in this function, when we pass this coordinate will not be a normal coordinate, but it will be Earth engine data type. Yeah. So in the next step, I'll try to explain what this code is doing. I have created one feature class, so which is a very empty list, and I want to add all the coordinates available here. So in this step, here for key comma value in element dot item. So it means previously we have this map dot draw control the data, means this earlier step, this has this following data, but if the key and value, so it will try to extract the key and value. So what does key and value mean? So this first part is called key and the other part is called value. In this case, the geometry is the key and the data inside the geometry is the value. So there is two kind of data here: type, properties, geometry, which are the key, and all its information are the values. So from each element, it will try to extract key and value. And if the key is equal to geometry, which means in this case, if the key is equal to geometry, then only save that coordinate information. Which means ignore all other features, because it is not needed. So if you see here, I have tried to print a dictionary that the data that we get here. So it is only getting the geometry value now and ignoring all other value like type and properties. Yeah, so this step is doing that. It is grabbing all the key and value, and it is comparing. If the key is equal to geometry, then only save that data. And in the end, I will append this feature. I will add this feature to this feature variable. So it means feature.append this dictionary. It means I'll add this dictionary to this feature class. Now if I for a moment, I will turn this off and plot only feature. So let's say if I do print features, and now the feature will have this information. But if we initially we initialized feature as an empty list, but after this we have some information here. So now let's close this. And the second step, as I mentioned, that coordinate, all the coordinate that we collected here is a simple normal x and y information, like just a number. But our Earth engine does not know if it is a coordinate or not. So we have to convert it into geometry type polygon in Earth engine. So to do that, we select this feature 0. It means select the first feature and select the geometry. And inside geometry, select only the coordinates. So there is type and coordinate information, and we only want these coordinates, and the rest of the information are also redundant. We don't need it. So we just pass the coordinate, and hence this AOI will be initialized. Now if I run this code, then you can see the polygon type is displayed with the coordinate, this coordinate. So now it is well structured. So any issue with this code? So basically, whatever area of interest that we draw here, it has several information. So we do not need any other information. So we get rid of that first. and we just try to get this coordinate information initially, and after we get the coordinate information, which is here, we try to convert that to Earth engine data type. Yeah, so if it is clear, we can go to the pre-processing step, which is the next step. Yeah, please let me know if you have any issue running this code or not. Okay, I'll move on to the next part. So the next step is cloud masking. So cloud masking, the basic concept is in the optical sensor, whenever it takes the image, if there is a presence of cloud, then that cloud will also be captured, and hence it will block the view on the surface of the Earth. And that is a big problem when working with the optical imagery, and it will create challenge in image analysis as well as interpretation. So to do some accurate analysis, we need to remove those cloud and shadows. Yeah, so in this step we are trying to create a cloud mask, which means we take an image and we remove all the part of the image that has presence of cloud, and basically the output is it will create a hole in an image, so you will only have cloud free part of an image after running this step. Yeah, so I'll explain this code block, what it is doing. So this is a function. uh, so if you run this code block, it will do nothing right now, because it is only a function and you have to apply it on some data set later on. So if you pass an image over this function, then it will select a QA pixel, which is a quality assurance pixel, and there is also this RAD sat pixel. So there is two additional band in Landsat image, which is for the quality assurance only. So this is doing a bitwise operation and removing all the images that does not have a. So this QA mask is doing the cloud removal, and this RAD sat band is doing saturation. So if the image is not well saturated, it will assign it as a 0 value. It will remove that value, and so it will create a binary image like we did yesterday. So if the quality of an image is good, it will create as value 1. If the quality of an image is bad, if a pixel is not good, then it will create as 0. So all the pixel information that has a 0 information will be eliminated from the final output. And as I mentioned earlier, the image also has to be scaled down. So we will multiply it with a very small value, so that all the value will be a very less. All of them, I think it will be less than 1 after we do this processing. So there are two types of band in Landsat, which is SRB format, which is for the optical band, and there is also a thermal band, which is ST, starting with ST. So we multiply all these with a very small number. So to know how I get this number, we have to go a little bit up, and when I explain this scaling factor, so there is a USGS documentation on it. See, yes, yeah, this is the documentation page where it says if you have a collection to surface reflectance data, then you have to scale it using this, and the additive offset is minus 0.2. If you see my code here, I have implemented the same. I mean, yeah, here you have to first multiply with this value, and the additive factor is minus 0.2. Here, multiply and then add with this. And similarly for the surface temperature data set, the multiplication factor is 0.0034 and all, and the additive offset is 149. Yeah, so this will do the scaling of the data set. Yeah. When we see the final output after applying this algorithm, then we'll try to understand what is happening here. And because initially we just take the Landsat image, which is a normal image, which has presence of cloud, or the image can also be unsaturated other times. And from here we are applying the optical band. So with this optical band means the scaled version of the image, and this is the thermal band, which is also scaled version of the thermal bands. And second one is update mask, and this update mask for QA mask, so which means it will remove the remove all the areas that has a value 0, which means the presence of cloud. And the last step is saturation mask. It means it will remove all the data information in the image that has a very poor saturation. So it means both of these information, both of this algorithm is trying to remove all the unwanted pixel from the image, unwanted, or let's say cloud, presence of cloud, or bad saturation. Yeah. And as I mentioned here, this is for Landsat 4, 5 and 7 surface reflectance, and the code is a little bit different in case of Landsat 8 because it is a different kind of sensor. Most of the time the multiplication and additive factor are same, but I think the issue comes here. Yeah, we have to apply this integer instead of ee.number.parse. So it is the same thing, but I don't know why this Landsat 8 does not take this calculation, but it takes this one. So this information is also available in Google Google Earth Engine documentation. So if you see, these functions are already available there. So this is from where I inherited this code for cloud masking and scaling. So if you can run this step, it should not give any error because we are not running it yet. It is only definition of function. In the next step, we have in the next step, we have this test code where we are trying to apply all the function that we created earlier. So let me explain this one. So in the first line, as we did yesterday, we are yeah, if you have any error running with the running previous codes, just let me know. Yeah, so this one is taking Landsat 5 data collection to tier 1, and we are trying to filter that filter first and second month of 1995 within this date range for Landsat 5. So this so the Landsat 5 collection has numerous images, but this is trying to limit that collection to this date range first. And the second step is filter bounds by AOI. It means the area of interest that we draw earlier here, whenever we select the 1995 January to February image, it will give the collection will load for whole world, but we only are interested in this particular area of interest. So in this part, we are trying to filter the bounds on area of interest, and this step is trying to filter the cloud cover to less than 10%. This we also do this code yesterday. So filtering the cloud to 10%. So the maximum limit of it says greater than, so it is an error, but it has to be less than. So you can also later understand, if I use greater than, then it will have a different consequence. It will have a more cloud presence, at least 10% cloud presence in this case. But if we make it less than, then the maximum cloud that can be allowed in image is 10% over the whole scene. So yeah, let's do greater than and see what kind of image we get. And this one is map function that we did yesterday. So let me show you what we did. It becomes easier to understand. Yeah, this is the mapping function that we run yesterday. So the logic is, if there is a certain function, so in our case the function is to eliminate the cloud, right, and to do the scaling. So if you want to apply that to several list of images, then you can use the map function. In yesterday's session, we did simple thresholding. There was a simple function, and we mapped all the Landsat collection. So the collection, image collection, means there are several images, not single but several images. So from this collection, you will run this algorithm, and it will also produce the list of output. So if you want to work on large amount of data set or the whole image collection directly, then you can instead of applying individually on single yes, instead of implementing the algorithm on single images, you can apply it over the whole collection. So that is a really convenient way of applying an algorithm over over the whole collection. So what we are doing, we have image filtered by date, filtered by bound, filtered by cloud cover, and we still have like 30-40 images probably within this time frame, and we try to use the mask algorithm. So here I use mask L457. So as you see here, for Landsat 45 and 7, so it will apply this algorithm and not this one. And map, and you have to pass the algorithm also. And finally we do the median. So it means now even after completing this step, you will have a stack of images over one another, and we just combine all of them. And for each pixel, if there are like 4 or 5 images, then we just combine all and calculate the median. So statistical median for that individual pixel. So after that, you will get a one image, and it is continuous. So this step we are trying to visualize. Now let's run this code and see what will be the output. So if you see here, we already have loaded the Landsat 8 image, but it is not what we are used to seeing. So in this case, you can see several holes, presence of holes. Why is it so? Because I have selected the cloud cover greater than 10%. So it means that each image has more than 10% cloud cover. So this area was completely covered by cloud, or the saturation was not very good. And so our function eliminated this pixel values. So if I reduce the cloud cover to less than 10, then probably this will be more filled image. Yeah, so it looks more continuous because we selected only images which has very less cloud, and the chances of being eliminated, those pixels being eliminated, is very low in that case. So now it is more continuous, and you can see the image is also very cloud free. And since we loaded image collection, so there should be several images, but if you see here, this is a single image in the end. So this is due to the median function here. So what it does, as I explained earlier, it tries to combine all the pixel and only calculate the median, and only give you one value based on the statistical median. Yeah, this is the kind of images we create before we do the analysis. So if we are comparing annual change in surface water or any other parameter we want to study, then we create an annual composite. So how, and see how, or seasonal composite, like for 3 months or 6 months, and then we try to see the changes between those period by creating this composite. So this is more higher quality data with the absence of cloud, snow, and yeah, cloud and snow. So next step, next step is the exercise. If you have no issue running this code, then you can try this code here. So I'll just make it greater than for a while. Right. So it has many holes. So here I have said try changing the start date from 1995 to 1993 and see what do you notice change. So use the same code block, but just change the time frame as mentioned in the question, and let me know if you can run this script or not. So here the starting date is 1995, between 1995, but if you change 1995 to 1993, you will see a different kind of image. So yeah, let me know if you can run it or not. If you have any queries, please feel free to unmute or drop the question in chat. Okay, let's have 2 or 3 more minutes here. Yeah, the question is asking to change the start date from 1995 to 1993 from the previous exercise from this code block. So Yeah, let me copy it, and I'll let you know where we have to make changes. So here in this start date, we have to change it to 1993, and you can let other dates same. Basically, it's a simple question where you have to change this to 1993, and then let's see the result, how it will differ from the previous one. Okay. Yeah. If you see here, that now we have loaded more than 2 years of data, and yeah, more than 2 years of data. And previously, when we removed the cloud in 1 month image, then maybe there were 2 or 3 scenes during that time period, and within these 3 scenes there is very high chance there was cloud in this area, and uh, the algorithm completely eliminated and there was no pixel to display here, so it became transparent. But when we go around 2 or 3 years or even annually, then there are some pixels that does not have cloud on it. So that's why this image is now more filled. I think it's completely filled in our case. So this is the kind of image that we use for analysis in the later part. Yeah, there is a second question here to select and visualize the NIR band from image. So here we are visualizing all 3 bands, but it is like a revision to yesterday's part, where we only want to select a single band, because in this section we are trying to calculate the different indices like NDVI or MNDWI, and those indices require that you should be able to select a single band for analysis. And that's why uh, you just have to make change in this first line here, and there is also some hint I think here. You have to use the select function, so just uncomment it, remove this hash sign, and add your code in this highlighted part. If you want to know what the NIR band means, so because we want to select the NIR band, so there is a link here. So in this link you will find information for Landsat 8. What does NIR band mean? So it means band 5. And if you do not know how the naming convention is for the current for this imagery, you can also show the list of band that is available. We did this I think yesterday also. So let's try to see what are the band available to us. So because this is the image, we want to change the image name. Yeah, so if you see here, Landsat 5 collection test is our final image, and we want to see the list of bands here. So let's see. So the band 5 means SR underscore B5, because the counting is starting from 0, so the fifth one is the 4 here, SR underscore B5. So if you just replace this code with SELE select, and on single quote if you put SRB5, then this will, instead of taking the whole 18 or 19 band, I think, yeah, there is 19 band total, it will only select SRB5, which is the NIR band. And let's see, this is the NIR image. Yeah, so we are almost completed the first part of this session. So let me know if you have any queries up to this point, so we can discuss. And also if you have any issues in running the code up to this point, then let me know. Can you confirm you can run the code or not? Uh, are you able to follow up to this point? Yeah, or can anyone share your screen and show me what your result is for this part, if you have been able to follow? So yeah, so if you have any questions up to earlier steps also, like the method of identifying water body pixel, water bodies, and whatever method I have explained earlier in presentations, you can ask from this part also. And up to this point, I will do a quick revision. So we have not actually entered into the part of water extraction, but here we try to understand what data we are using. So we are using Landsat series dataset, and for different years there are different sensors, different Landsat series data available. So if we are doing 1985 to 1995, we are using Landsat 5, and 2000 to 2010 Landsat 7, and beyond that Landsat 8 and 9 are available. So for this training we are using 5, 7 and 8 because we want to understand the surface water change from 1985 to 2020 on every 5-year period. So this is our study area here, and as you can see, between 10 years the surface water has almost completely disappeared. We can say it has disappeared. So we want to see, or we want to quantify what is happening here. So yeah, so we want to calculate the area and see the change. Yeah, this is the preliminary step of initializing Earth Engine and sorry, some basic libraries that is needed for the project. And the first step is to initialize this map and get the area of interest. So in this stage only I already selected all the visual parameters. So to produce a natural looking color, we have this band information. We have to set 3 bands in order like red, green and blue. So in Landsat 4, 5 and 7, band 3 will represent red, 2 will represent green and 1 will represent blue, red, green, blue, in that order. So we use this 3-band combination to produce a 2-color composite. But in case of a Landsat 8, we use band 4, 3 and 2 instead of 3 to 1. Okay, so that is the difference. So we have 2 different visual parameter. And I also explained this part, which is the minimum and maximum values. So usually, typically the range of Landsat is from 0 to 65,000. But if we use that whole range of data, then the contrast of the image will not be very good. So we just want to improve the contrast of image. So there are several techniques to do that. We can apply stretch function, or we can also do some histogram based thresholding. But instead of that, we use simple technique like minimum and maximum value. So we just remove all the data that is on the extreme corner, which is bright or dark, and we just take the range of data. In this case, 0 to 30,000, which will produce a very good contrast. And if you see, the same visual parameters is repeated twice, but with this SC in the front, which means the scaled version. And as I mentioned that the original data is difficult to do calculation. So to optimize that, we have scaled the data set so that it falls in range of 0 to 1. The calculation becomes very easier. So this is the data normalization step. So even if you are working with machine learning or deep learning, any kind of classifier, this data normalization is a very important step. Yeah. And yeah, the area of interest that I draw here, we have to extract the coordinates, only this coordinate information, because there are a lot of unuseful information on this when you draw this coordinate, this bounding box. So to extract this coordinate, this is the next step that we use. And even after we extract this whole data set, there are some other information that is not very useful, like geometry and coordinates, because we just want this number. So this next step is also trying to extract the number, and finally convert that normal xy coordinate into Earth engine data type or Earth engine polygon type. So ee.geometry will create Earth engine geometry type, and the type of the geometry is polygon. So instead of this, if you make it multi-line, then it will create the closed loop of line, but it will not create a polygon. So that there is some difference with this one. So yeah, because we want a bounding box, we need to create a polygon from here. And the immediate step, as I mentioned in my slide, it is image pre-processing or cloud masking. So the pre-processing step also involved doing some scaling, as I mentioned earlier, and removing the pixels where the information is not very useful or the quality is not very good. So for that reason, we eliminate all the clouds using the QA mask, which is also the band that is already available in Landsat image. And there is this RADSAT band, which is also for the quality assurance. And this quality assurance band will measure the saturation. If the saturation is not very good, then eliminate that pixel also. And yeah, after that we update the mask based on these two data. It means whenever the data has a very poor quality, we just remove that particular information from image. That's why in the next step we create hole in that image, because we update the mask based on this QA mask and saturation mask, QA mask and saturation mask here. And we add the band after we do the scaling. So it means all the data set that is already available in Landsat will be scaled and saved again. So let's say surface reflectance 1, surface reflectance 2, and all those individual band will be scaled now after applying this. And yeah, so this is the test image where we want to check if this algorithm works or not for the immediate next step. So we load the image collection from Landsat 5, and then we filter it on date, this date range, and we also filter based on area of interest, because we only want the data set which is within that lake, and not global data set. And after that we filter the cloud cover. In this case it is greater than, but you can use less than. So because I want to show you how this wall will be created in case of when there is a cloud. So yeah, if I exclude using this algorithm, let's say this map algorithm, and if I run this code, there is an error. Okay. Go to this animation. Okay, it works now. Yeah, because the image scaling is also skipped. Let's try. Yeah, this is the image that you get. It is very cloudy in this case. Yeah, this is what we are trying to eliminate. So if we now use that function again, this map from this algorithm, if we implement that, then you can see this, all these cloud pixels will be eliminated right from here, and immediately it will take the median. So whatever is available in the next image, it will try to get that information. Let's try to run this, and this is the clean image. So this image was completely clouded in the previous one, So we completely remove that, and there is no replacement for that now, because the time range is very small. If you take a 1 year image, then there will be some images which does not have any cloud, and then we can see a very continuous image as in the next step here. Yeah, so this is what we have completed up to now. So I think we can take a 15-minute break, and after that we can continue the session. Let me know if you have any issues up to this point. Okay, see you all after 15 minutes break. And now let's check your time. So it's almost 11. Let's see at 11:15. So, hello everyone. I think the break time is ended, so let me know if you are here. Yeah, Isafi. So I think I'll have to check the time, but in this script, I think I used the Landsat 5, right? Let me check. This part. Yeah. So I think the Landsat 5 was not there in 1980s. So let me check the time frame. It is Landsat 5. It's from 1984. So you'll only get data from 1984. So the earliest you can go back is 1984. But if you want to use before this, then you have to go with Landsat 4, 3, likewise. Yeah, just let me know when I said begin. And if you are there, then yeah, you can begin. Okay, I think we can start now. So yeah, already up to this point, we have already loaded the test data set, and we have performed cloud filters, and also filtered by date, and created a composite like by performing a median. So all this thing we already performed, and now this image is already ready for the next step. So the next step is which yeah, so the next step is water body extraction. So now we already have prepared the image. Now we try to extract only the water body from the images. So we are following this indices based method. So as discussed, there are three different methods. So we'll go with the special spectral indices based method for this one. So okay, let's go to next step here. Let me explain some of this thing. So water body extraction method include water body extraction algorithm, and based on band combination. So single band threshold method as discussed earlier, or multi-band spectral relation method. So there are also other method like water index method and thresholding method, and machine learning algorithm like SVM, random forest, and deep learning. So this in detail we have already studied. So but for this particular instance, I am using indices based, which will utilize the combination of MND, WI, NDVI, and EVI. So these are three different vegetation indices that we are going to use. So here I have put a reference paper from where I have just a second, from where I have taken the reference of this whole code. So let me show you what this paper has. Okay. Okay, so in this paper, the author has actually used this formula for water body extraction algorithm. He calculated MNDWI, which uses the green band, short wave infrared SWIR, and green plus SWIR, uh, green minus SWIR, and green plus SWIR, and he has divided it. Similarly, in NDVI, as we also discussed yesterday, the nominator is NIR and red band. We take the difference from these two bands, and NIR and red band is added in a denominator. Similarly, this is a formula for enhanced vegetation index, where we use NIR and red band, and also we have blue band in this formula. So this is a little bit complicated to see, but it's also simply it can be simply integrated, implemented in our code. And the final criteria is by combining all these indices that we calculate, we can derive the water body. So he uses this criteria. If a pixel meets all the following criteria, and the criteria is EVI is less than 0.1, so the concept is that all the indices will have a value ranging from -1 to +1. So that's why if the EVI value is less than 0.1, and so it is a AND operation, so it also has to, this has to occur, and also the second part of this AND formula, the second part also has to happen for it to be a water body. So both these criteria has to be fulfilled. And the second criteria is MNDWI, or modified normalized difference wetness index, has to be greater than EVI. It means the wetness index has to be greater than the EVI. So EVI is vegetation index. So it makes sense now, because only if in that particular pixel, when we are comparing, if the wetness index is greater than the vegetation index, then that can be classified as water. Or means in two cases, either one has to be true, right? So, or if this does not happen, then the second criteria can also make it true. Like if the normalized difference wetness index, same as here, is greater than normalized difference vegetation index, so in this case also it will become true. So the overall, this formula is trying to say that if enhanced vegetation index, I mean the first step, if the vegetation index is very less, then it can be water, right? And if the wetness index is greater than the vegetation index, then also it can be water. Or if the MNDWI the wetness index is greater than a vegetation index, then in that case also it could be water. And this uses and, it means both of the criteria has to be fulfilled in order for the pixel to be water. So that is the main concept. And yeah, basically we'll use this logic to implement in our code here. So here I have just taken this formula, EVI less than 0.1, and this formula, the second part of the formula. And in our case, this MNDWI becomes this green minus SWIR divided by green plus SWIR. Whatever he mentions here, the same thing is written here for your reference. And if you want to know more about such vegetation indices, there is this link where you can find a detailed information on several vegetation indices. Like all of these list in this table are different vegetation indices used for different applications. So I think there are hundreds of vegetation indices here. And yeah, so this is our implementation. So water mask implementation, where we create a function. So in this function we pass the image, which is our annual composite Landsat image. So it is a cloud free image, and for your reference, it is also a scaled image. As I mentioned earlier, scaled image means the data is not ranging from 0 to 60,000 in any pixel, but it is ranging only between 0 and 1. So all our formula, if you see here, we need green, SWIR, NIR, and red, and also blue. So I take only this 1, 2, 3, 4, 5 band as an input instead of all the band from the image. So yeah, so this is the function where I implemented the NDWI, right? So if you see, yesterday we implemented the expression function like this. So we calculated simple NDVI using this formula, which takes NIR band minus red band and divide by NIR band plus red band. So this is from the yesterday exercise, and this expression does not know what is NIR band and red band. That's why you have to explicitly mention that NIR band means from the image you have to select SRB5, or band 5 is the NIR band. You have to assign that in this step. And so the red band also is assigned likewise. So because for NDVI we only need NIR and red band, we could pass 2 and it would work. But in this case, we are passing many 1, 2, 3, 4, 5, total 5 band, and we are performing calculation. Now if you see this NDVI part, it is same as what we did yesterday. Right? Image.expression will help you to write a complex expression. So there is also a second way of writing mathematical operation in Google Earth Engine, which is directly using these formulas like EVI is less than 0.1, and so these are some basic operations. So instead of it, if you want to do addition, you can write ADD or SUB for subtract and all those functions that is available in Earth Engine by default. But to write more complicated formulas, I usually prefer this image.expression tag, this function. So you can directly put in all the variables according to the formula, as you see here. For MNDWI, it's green minus SWIR, green band minus SWIR band, and green plus SWIR here. And because our code does not know what each of these band means, we have to also assign image and select the green band. This green band information like SRB5, SRB4, all this data is in this function itself. We have to pass when calling the function. So if you see here, the marks water function, to quickly review, it takes image and all the bands, right? And then we perform 3 different calculations: MNDWI, NDVI, and EVI. Yeah, so after performing this calculation, the final criteria has to be made so that it will be classified as a water body. So the criteria is implemented here. EVI is less than 0.1. This was the criteria, right? First block. And so this and is mathematically expressed as .and. So if you put it as and like small case here, it will not work. So it has to be same. So and also MNDWI is greater than EVI. MNDWI is greater than, this greater than will be represented by .gt, and this or will be represented by .or, and MNDWI is greater than NDVI, So this is the complete logic of the program. that will extract the water body. So in my earlier presentation, as I said, there was a single band based method which will just apply threshold on a single image, but spectral index based method can utilize spectral index, single spectral index like NDVI or NDWI, or it could also be a combination of multiple spectral indices. So in our case, we use multiple spectral indices because the paper that I took reference, it had a very good result by combining all these spectral indices. Okay, let me run this. And the next step, because in the earlier part when we selected the Landsat data, it was only for the test purpose, but now we select Landsat 5, Landsat 7 and Landsat 8 collection for our study purpose, which means for each year we will select the image data set. So this line of code is repeating here. It means I am taking Landsat 5 collection. This one is a tag. So this dataset tag I got from this Google Earth Engine dataset catalog here. If I go to Landsat 8, the surface reflections data we are using, and tier 1 is a good quality data, and relatively low quality data are in the tier 2. And if you see this one, Landsat, this is the code that I use here to identify that collection. And we do filter bound as in the earlier step, and also we do filter by cloud cover because we want the maximum cloud to be 10% or less. So in this way we filter the Landsat 5 collection. Similarly, we take whole Landsat 7 collection and filter again, and then again Landsat 8 collection and filter. So this is like only taking the collection for now. In the next step, we will implement more complicated algorithms. So let's run this. So it should also run without any issue. If you want to display what is the information on any of these images, let me display for Landsat 7 collection. I will add a code here to display Landsat 8 collection. Let's see what is in there. I think the dataset size is huge, so it will take a while. Yeah, because it will take a while, also because we did not provide the time parameter here. We did not filter by time, right? So it is taking all the Landsat 8 archive from all the years and only trying to filter based on the cloud and area of interest. So yeah, there are 760 elements, but we do not need all of this data set. So yeah, so we'll apply more filters down. So in the next step, if you can run this, I will paste this code in the chat. So if anyone wants to try, how many images are there in your collection? Yeah, you can also check. It will vary because your area of interest and my area of interest is different because we draw a rectangle manually. That's why. In this step now we do some pre-processing. So in the when we defined the function for doing this masking and scaling, we did not apply in this collection, right? So this collection is fresh, so we have not applied any algorithm over it. So I'll try to explain what each of this code block does. So if you see here, this water mask is an empty dictionary for now. I have not initialized it, and I will whenever I run this code, I want all the water mask for each year, 1985, 1990, 1995, which means the water mask means something, the image will look something like this. It means all the area which does not have water will be one color, classified as one value, and if there is a water, it will be classified as a second value. So we want to create this image and we want to save it in this dictionary here. Just one moment. In this dictionary, water mask, in the pre-processing step. Now what I am doing is for year in range 1985 to 2025 in every 5 year. So it will take 1985, 1990, 1995, every 5-year interval. I'm taking the years, I'm running the loop, and first I take the image collection for that year, right? So for if it is 1985, 1990 and 1995, I will use Landsat 5 collection. So this function is doing that. In case of this year, it will first replace by 1985. And in second case, when it runs, because it is if, it means our looping statement, and in 1990 it will again run this script, and if it is 1995 it will again run this script. Okay, for 3 consecutive time frame we will run this script. So how do I know if I have to run this for 1990, sorry, 2000 or not? So this guide I have provided on the top of this page, because for 1984 to 1990 we will use Landsat 5 data. After going to 2000 we are going to use Landsat 7 dataset, and so on. So same thing I implemented here. So if year is 85, 90 or 95, run this one, and we filter the date that each year, and then we apply this algorithm, cloud mask algorithm, as in the earlier step, the same step, and we do median, which means because there are stack of data filtered in our filter criteria, so we just filtered by date here, and then so there will be like 10s or 20 30 data set in every single point. So it will just combine all the data statistically. So if single pixel has 5 value, then it will try to take median value of those 5 value and create it in the final pixel and store it in the final data, this image aggregate data. And since the image is very big, so our area of interest is very small, and Landsat swath can be a very big size, so we just clip that over our area of interest. So this is what this is doing, is this is clipping only up to that extent and excluding all the feature that is outside, and then we display that data. And if you see, this year is also coming from the same variable. This year is being used multiple times, and because whenever we save the data in the end, we want it to identify that data set, that water mask. So because when we have like 7 or 8 images, we will not know if it is from 1985 or 1995. So for that reason we have to also name that, and we have initialized a dictionary. So dictionary always has a key and a value. So the later I will show you what this key and value will look like. The key will be the year and the value will be the image water mask. So if you say water mask for 1995, then it will refer to the image of 1995. So yeah, this is for that purpose. And I'm calling the water mask function here because here I created the water mask function, but now we have to run it over each and every image, right? So I call the water mask function here, and I pass this filtered image aggregate here, and I pass the information on band also. This SRB1 means blue band, green band means SRB2, and so on. So because our function needs this information on which band SR_B1 what it refers to, so that information I have to pass so that the image can use that information down here. This algorithm can use that information. So that is the whole logic. And if you understand this first block, then the second and third block are just the repetition. For 2000, 2005 and 2010, which I use Landsat 7 collection here, right? And the third band, the third information here is for 2015 and 2020, which uses Landsat 8 collection. Now if I run this code, I should be able to see this image band for each year. So this is the annual composite for 85, 90, 95, 2000, 2005, 10, 15 and 2020. So this image composite is already created. So I want to know if you have been able to run up to this point, because yeah, this is the image pre-processing, and this pre-processed data we are going to use in the next step.
I didn't understand, to be honest, the first before this one, the step before this one. The step after that image. Should I copy this 3-line one, or should I copy this whole line?
You mean this one, right?
Yeah, should I copy only this one, or should I also copy the bigger code upper of this one?
For this one, right?
Yeah, should I copy this one?
Yeah, you need this. So I will try to explain this, what this means, so then you will understand.
Is there any code behind, like before this also, or not? I missed the first.
No. From this point, we just start from this point, but
Okay.
you will need some visualization parameter to visualize the image. So
Okay.
let's say this part we need later on also. Yeah. So if you have access to the notebook, then you can run sequentially and come up to that point.
Basically, I'm copying and pasting it into a new book, because in there it gives error. But when I copy it to a new notebook, In run it, then it runs. I don't know my issue. So I'm doing it that way. I
Okay,
open
yeah.
your notebook also in mine also, copying from your into mine, and then it runs.
I see. Yeah. Okay, so if it runs in your, then yeah, you can follow by copying this also. It's fine. Yeah. So the main concept is we just define the function here, and we implement this a water mask function, right? Because if you see the content of this function, it is only taking the image and applying our formula, as we saw in the other research paper. So that said, the water, the pixel can only be water if its EVI index is less than 0.1, and other this criteria is also fulfilled, like MNDWI is greater than EVI, or MNDWI is greater than NDVI. So this is just a mathematical operation that we want to perform, and similar to yesterday when we calculated NDVI, the other formulas can also be implemented here, like how to calculate MNDWI, because you already know the formula. It's green minus SWIR. For NDVI, it was NIR minus rate divided by NIR plus rate, and so you can implement this formula in this expression tag. So here, here, and here. It's basically the same thing here. Like if I'm calculating NDWI, is green minus SWIR, green minus SWIR. But yeah, so I code this function first, and then for because I have several Landsat scene, so I'll have to pass. So instead of passing individually, so if I write a function, then it becomes a reusable piece of code. So now I can just pass in image, and this function will do its work and give you the result. So that is the whole concept. And the after calculating these indices, the criteria has to be made to be a water body, and the result of this calculation is only water body if that pixel will represent water body or not, right? So if we do this, we'll understand if that pixel will represent water body or not, and then we return that to whichever code is calling that function. And this is just a function, so by itself it will not work, so we need a data set to pass here. So these are the three, because we are looking into a long-term data. So Landsat 5 does not cover up to 2020, right? So we are trying to load all the Landsat 5, 7, and 8 data set. So because the time extent is very huge from 1985 to 2020. So that's why we loaded the data here, the image collection here. And we did not perform any other filter than area of interest, which means over our boundary, our lake boundary that we draw in the previous step. So all the Landsat image has to be within that range, and also the cloud cover cannot be greater than 10%. Here I say that filter cloud cover less than 10%. So it will only take images with less than 10% cloud cover. So this is only taking the image collection, but now we have to apply our cloud masking algorithm. So this step is additional filter. So because I want to also filter the date, so let's say I want to map the water boundary for 1985, then I need only for the images from 1985. So this code here is taking the whole Landsat 5 collection here and mapping it, filtering it for the range of 1985 here, because this is a looping statement in programming. So every time it runs, first it will take 1985, second time it will take 1990, and third time it will take 1995, and instead of this year variable. And here it will take this 1985 value, second time it will take 1990, and then again 1995 here. And because we already wrote the algorithm to remove the cloud from the image, because this image has a lot of cloud. Even if we say 10%, the 10% of the cloud can also interfere with our analysis. So we apply this cloud masking algorithm here by individually. So if there are 100 images in 1985, then we have to run this 100 times. So this mapping function will already do the task. If you, yeah, it's also coming from yesterday's material. As I saw this one, so it will take individual image, and whenever I run this function, then the whole collection will produce the list of outputs. So instead of running one by one, all the collection will be processed at once. So that's why we are just implementing this. So it is very quick to implement. And then we use median and clip. So if you see what I have done here, I have done the same thing that I have done in the earlier step. Here, yeah, I took the image collection, I filtered by date, I filtered by bounds, which is our area of interest, and I filtered the cloud cover. In our case, it is less than 10%. And then I did apply the algorithm for masking out the cloud, right? Masking out the cloud means remove all the pixel that has cloud on it, and okay, this like this. And the next step was to take the median. So because there will be hundreds of images that will fulfill this criteria, because the Landsat is taking a few images every month, so we'll take the median. So it means if there are 5 images in the stack left after doing all this filter, then it has to combine all and produce one image. So the combination takes either mean, median, average, anything that is specified here, but in our case we take median composite. So it will try to take the median of all the 5 pixel over the 5 different images, and then give you one single image now. So this all is not 3 or 4 images, but it is a combination of all those images to form one single image. Now from the collection we are getting a single image. That is the whole concept of this formula. And this we don't want to run that single time, but we want to run it for every 5 years. So I have implemented that same logic in the loop here. It's the same thing, but you have to run this code for 1985, 1990, 1995, similarly 2000, 2005, 2010, and so on. So this is the formula, but the last one function that I added was this mask water function that was not available in the earlier step. So what this function does is it will take the image and it will apply this criteria, the criteria that we define, mask water function. It will apply this criteria and give you the only the water boundary, and it will classify water boundary or no water boundary, only 2 classes in the image. So the final image will look something like this. So this one is the water boundary and detected water pixel, and outside it is non-water pixel. So this is the overall concept of our whole this implementation. So yeah, if you have any questions up to this point, yeah, please feel free to ask.
And if I remove that 5, like every 5 years, and I put 1, or if I don't, I put 0, will it run every year?
In which just a moment. Did you mean
the time step that you put every 5 years?
Okay, so if you want it, so you mean you want it annually, right? So from 1985
yes, right.
annual. Yeah. So where is yeah? So the only change you have to make is single year, right? And you have to pass in the list here, like 1985, and then again you have to also pass, because I only need 85, 90, and this one. Right. You have to pass 1986 in your case.
Okay.
Yeah, and so on.
7 and up to, right, for example, whichever date we want to run this, like yes, up to 1995.
Yes.
And then exactly. 2000 also 2001, 2, 3, 5 up to 2010.
Yeah, you can also run this annually, but
okay.
Yeah.
Thank you.
So if you see the we started off with the image collection and ended up with the image and water mask, right? So if you see here the properties, bands, then you have all the band information that we started with initially. But there is this is a single image. If it was an image collection, then it would be image collection and 750 images in that area, something like that. But we already did combined all those images by filtering and also applying the median composite, and we combined to one image in the end. So yeah, so it should be like this, like 760 element, but then after performing this median, we only are left with 1 images per year. Yeah. So yeah, I think you understand this concept. To understand this implementation, I have also created one more code here. So this is a test code. It is not being utilized in the next immediate steps, but to understand what this mask water function is doing. So it will first calculate MNDWI, as I said, NDVI, EVI, and then criteria, right? So let's run this test script where I have run for 1995. I have taken single month image. From January to February 20. Instead of this, let's take up to yeah, mid-year. And the cloud cover, and then this is the cloud masking algorithm, and we took the median as I said earlier, and then we clip it over the area of interest. So if the image will overflow outside the area of interest, it will be clipped. And then we take all the returns here like water body, MNDWI, NDVI, and EVI. So whatever is being produced inside this function, we are taking it for visualization. Let's try to run this, and it will be easy to understand. Yeah, so the FF function is generating these images. So the first one is Landsat A data, which is basically just an image. But if you see here, some pixels are transparent. It means those pixels were cloud or the quality was not very good, and hence our algorithm removed those pixels completely. And the second one is water body, which is the required product, right? So if you see here, the white pixel will represent the lake. So let me zoom it in a little bit. And if you close this water body, you can see the edges has been accurately accurately detected as water body. You can see a small river here. Even in the optical image, we cannot see very properly, but our algorithm has already detected a river. Even the subtle water bodies also. So you can guess that this algorithm is performing pretty good up to this point. And the intermediate data sets were NDVI, right? So if you see this NDVI map, NDVI usually represents the vegetation, and also EVI will represent vegetation. Okay, let me go to the setting. The NDVI value will range from it has a greens, let us apply green. Okay, so if the value is towards 1, it is dark green. But if you see here, the surrounding area is not very dark green. So it means the vegetation is not that much. So it is around this area. It means the vegetation is very low in the surrounding. But even when you compare the surrounding with this water body, the NDVI value is even less. So it means this area was already detected. You could already suspect that this area could be a water body because it has very low NDVI value. Similarly, the second step is MNDWI. So if you see these indices, then you can see this detect the water body very clearly. Yeah. So this is the normalized difference wetness index, so or water index, I think. So whenever it detects water, it will have a high value, opposite to NDVI, right? In NDVI, if it has a vegetation, high value of vegetation, higher vegetation, then there will be higher NDVI value. But in NDWI, if there is higher wetness or water body, then it will be detected as it has higher value in MNDWI. Similarly, enhanced vegetation index also, it has a higher value if there is more vegetation, and towards negative if it has a low vegetation. So in this water body area, okay, let's apply some. Yeah. In this case, if the vegetation was very high, it would be red, but it is almost green. It means the vegetation is also negligible, but the water body, it is towards negative, right? So it can be identified as a water. So only using a simple threshold over NDVI or MNDWI or EVI also, we could detect the water, but the accuracy would not be very good. So we use the combination and the criteria given by the author of that paper, and hence we derive this water body, and you can see the result is really good for this year. Right? But the problem is these gaps in this case, because we use the very short time frame, so the data is very cloudy. So in this case, we have to increase some time frame to create annual composite. So let's create until December 31 for whole. It will take whole annual images now from January 1st to December 31st in 1995. If we try to run this now, the gap is still not filled. So this is also one of the reason I have taken 2-year composite in the previous code. If you observe properly, this was in some of the year there was no cloud free images. So here I have taken year -1 and year +1. So it means if the image is for if we are doing analysis for 1985, I am taking all images from 1984 to 1986, that time frame, 1 year below and 1 year above. For 1990 analysis, I am taking images from 1989 to 1991, so within that range, because of this gap. Yeah. Okay, so here I have just, this is just a screenshot of how you can change the layer. If you feel confused later on, you can just click on this icon, and then you can turn off and on the layer from here. This is the original image. As you can see, this blue is the water, surface water. Okay, and I also mentioned earlier before running this task, there is this water mask function, which is water mask variable, which is completely empty now, and I am adding all the data set. There is two data set actually. One is the image data set, the image that the Landsat image, and the other one is the water body. This water body. So there's two images. So I want to see the content of water mask. So what we filled in there. So we filled in every year. So this is the key from 1985 to 2020. So this is how we can refer to these images. We can call it by this name. And there are two images object here, this one and this two. The first one is the satellite image and the second one is the water mask, in the same order that I saved. When saving, I saved it as, one moment. Yeah, when I saved it as image and then the water mask, right? So it is in the same order. Let's try to run this code. I think this one should run and it should give you this information. So unless you get this information, like for 1995 there is one image and two images. Yeah, unless you get this information, you cannot proceed to the other step, because you need you need the water boundary to do the analysis of what is the area of the total area of water in that particular year. Can anyone, yeah, are you able to follow up to this point? Yeah, should we move on to next step or? Right, so I see the message, yes. Okay, so the next step is, after you process all those data set, we want to visualize the data for, let's only visualize for 1990 now, but later on we visualize for all the years that we did the analysis. So we use the GE map, and then we add two layers, like the first one in water mask is represented by index 0, like water 1990, and if we give 0, then it will take the satellite image. And to visualize the satellite image, we have to pass the satellite image visualization parameter, right? So we defined earlier, and then we name that layer as satellite so that we can identify. So we'll see how that will be available here. Go to city. I think I have to run this first. Okay. Yeah, so the satellite name is same as here, and this water mask is same as here. So whatever you write here, it will appear here for your identification. So if I write satellite for 1990, right, and water mask for 1990, then yeah, it should be renamed as satellite 90 and water 90. It's the name, visualization parameter. And in the second one, there is a water mask. So it means either it's water or not. So we use the color palette. So there is two color palette. Light blue is for no water, and this dark blue is for water. So these are the two color palette we use for water mask. And if you see now, if you are at this stage, you can zoom at some levels and you can turn off the water mask and see that our detection algorithm has performed very good task in identifying even the subtle edges and boundaries. Here you can see, yeah. So the water is being detected well, I would say, from this, yeah, and even the river, yeah, it's looking good. So now I think after you do this preliminary check, we have not performed any kind of accuracy assessment. We are just visually inspecting if it is giving a good result or not. So now we can load the data. Okay, for the comparison, I am comparing it with 2010 because by that time the lake has completely disappeared, right? So let's compare with this one. This one is only to compare the previous data and the new one. The water is only around this area. Let's see if that is the case. Okay, so this area is detected as a water, but there is also no water in this area. So this is like a false prediction. So you can say that even this even after applying this algorithm, the analysis cannot be 100%. So you have to do accuracy assessment and you have to tune the model later on to make it more accurate, or apply some more indices combination, or if the result is very poor, then you have to move on to another step. But I think for our result, for our analysis, this is good. So this area might be there might be water within the 3 year period. So because we are taking the even the NIR band, and in those band it might be able to detect some wetness in that region. So even if we see in the image very clearly, this image is completely dry, but this area looks a little bit wet. So it might be some depression, and there might be some wetness in this area that is detected by our algorithm. Yeah, this could be one reason. Okay, so this is all the step on water extraction. So we move to quantifying this result, like what is the overall area, total area of water identify for each year. So that we are going to do next. But if you have any queries up to this stage, or any questions, any general question, then you can put in chat, or you can unmute yourself. Okay, otherwise let's move on to the next step. Right. So as I mentioned earlier, the next step is to vectorize the masked raster layer. So if you see, this one is a raster image, right? Now we want to create a vector, like a shape file from this output. So how to do that? Okay, first, because we are going to use this water mask dot keys very frequently in the steps below, because we have image, and each image we already name it with this value, right? So if you call water mask 1985, then it has two things. One is the satellite image, and other is the water mask. And even if you see in the earlier step, if you call water mask for 2010 and call 0, then it will save satellite image. It will display the satellite image. If you call water mask with 2010 value, and if you see the second, which is represented by index 1, then you get the water mask. So each water mask for each year has two data, right? So the first data is the satellite and the mask. So you can also see in the list, these are all the names that we iterate through and calculate area for these and all. So just for ease, we just put it in a list. Okay, so how do we so there are two concepts to understand now, that the yeah, this one I already explained, that there are two data in each individual, but there is also this step, this is called reducer. So the concept of reducer is, if there are so this is used for filtering the data in our raster, in our water mask raster, in this raster, sometimes the issue is like this. So these are the isolated pixel, which is unwanted for our analysis. So this small 1 pixel could represent water, but it could also be a false detection, and it is very likely that this single pixel could be a false detection in our case. So we will remove all this data set. So our the programming logic is that if you take this single pixel and see in the surrounding 5 pixel, and if there is water in any of the surrounding 5 pixel, and it's like a voting algorithm. So let's say if you take a pixel in this particular range, and if you see the surrounding, and if there is like 100 pixel that we want to compare, the surrounding 100 pixel, and if the 90 pixels says that it is water, and only 1 pixel say, 10 pixels say it is not water, then we will agree to the 90 pixels and not those 10 pixels. So that is the main logic. It's like voting. So if you see here in this example here, this is an isolated pixel which could be a false detection. So we take 5 pixels surrounding area, and we ask like if this is and then we ask if it is a water or not, and all the 5 surrounding immediate surrounding 5 pixels will tell that it is not a water in the surrounding. So it will say this is also not a water, and it will eliminate this output. So when we convert this to a vector data, we will not have a small shapes. Instead we only have one continuous shape. So that is the overall concept we want to do. And in the statistics, instead of taking the mean median, this kind of problem can be solved by taking mode. So the concept of mode is, if there is a highest repetition of certain values, then that will be the final value, or the mode value. So if you see here, this is the output that we produced in earlier step. This is the kind of output, and all these are data that has to be eliminated first. And the second thing is, even the surface that is detected as water is not continuous surface. So we want to apply some filter so that the result becomes this from this data here. So yeah, we want to fill in all these values. So how to do that? We will use the mode kernel. Yeah, ee.reducer.mode, and we use only the 5 surrounding, and we draw the circle around that pixel of 5 unit radius, and then we take the mode from that circle. Yeah. Okay, here is the implementation. So this is just a function. So as I mentioned earlier, the function is defined, but function will not run whenever you write anything. So even if I can write anything here, diff function, and if I write anything, I think it should not throw any error. Yeah, it will not throw error, because whenever you write a function, there is no error in the function itself. But when you run the function, when you call the function, and if there is error, then the error will come when you call it, right? So yeah, let me remove this now. So in this part also, whenever we call this, it is not running, but it is being called from the code below. So let's try to understand what this aid area property does. So in this part, after we create a vector data set, our data set will not have our data set shape file will have an attribute field. So in that attribute field, the area is not calculated by default. So we have to calculate the area and then store that area in there. So whenever we have this kind of a raster data set and we convert that to vector, we can it becomes feature, and the feature as a geometry. So it can be called by feature.geometry, and then this is the formula to calculate the area. But usually when you calculate the area, it gives you in square meter, and to convert that to square kilometer, we just divide it by this number here, so that it converts to square kilometer. Yeah. And after we do that, the area will be set into that shape file or the vector data set, and feature.set area is equals to the calculated area. So the field name will be area, and this area will be the value that has to be saved in the attribute. Yeah, we will see that in detail in when we see the output, we will see that differences. Okay, so now for watermarks.key, so which means for 1985, 90, all those keys, we have to iterate the same step. So it means you go for 1985, calculate the area, convert it to a vector data set, and then calculate the area and save it. So that step has to be repeated over all the five-year period. So as I mentioned earlier, this key list means this information. Yeah, and it will run for each year. And now this algorithm is implemented here. This one. So as I mentioned earlier, the algorithm has to be run only on the output, not on the satellite image, right? So I take the water mask item. So the item will represent the year. So let's say it's water mask for 1995, right? Then the one will take the output, not the satellite data. 0 will be satellite data. 1 will be the water boundary or the water mask. And this reduce neighborhood is to reduce operation. So this is the reducer where we can apply different kind of function. For example, yesterday we applied a reducer to calculate the sum for the population in whole province, right? But in our case, we want the reducer to calculate the mode or the maximum repeated frequency. So reduce neighborhood, and we use the reducer as mode and not sum. Yesterday we used sum, which does the addition, but today we use mode. And the looking area, so it has to look into the neighborhood, right? So reduce neighborhood operation looks to the at the neighborhood, and how far it has to look. It has to look up to 5 unit. So let's say if it is looking at this area, then it will draw a circle up to 5 unit, and then it will take a maximum vote, like if this area is water or not. And if many of the data set agree that it is a water in the surrounding, then it will also classify that single point as water, and it will run for all the points in this mask. So each and every point it will run, and it will later remove any isolated pixel, but because that does not agree with its neighborhood. And it will and the final output will be more continuous, right? So yeah, I think we implemented it here. Yeah, so after we do this kind of a filter, it will remove all the isolated pixel, and now I want to convert it to a vector data type. So here you can see ee.image wm. So this wm reduced is the reduced raster file. So instead of using the original water mask, which was stored in the water mask value, I use this reduced data type. So it means remove all the unnecessary data set. And that self mask that reduced to vector. So this reduced to vector operation is used to convert raster to a vector data set. And these are the parameter that we have to pass for this to work. The geometry is the area of interest, that is the maximum extent the geometry will pass. The scale is 30. So even for the vector, the scale value matters. So if you give 1 meter value, then whenever the line is being drawn, so it will be drawn at 1 meter accuracy level. So whenever you mention as 30 meter, then it will be okay. I think 30 scale 30 is good to go for this analysis. And these are other parameter that we have to pass compulsorily, but we have to look in more detail if we want to know about this. Yeah, and this will convert our raster data set. So the basic concept is, after we do the reduce to vector, the raster data set, which is in the image format or ee.image format, it will be reduced to vector at this stage. Yeah, so any question up to this point? So our idea is to convert raster dataset to vector dataset and remove all the pixels that is isolated or which could not be useful in our analysis. Yeah, and as I said earlier, this aid area property was not being used in the early step because we needed this vector data for that. And we map all this vector data set because let's say for 1985 there could be like 5 different ponds or 5 different lake area. So for each individual area we have to add the area property. So because our vector data set does not have any attribute earlier, so when we do feature.set, it will calculate the area and put it in the attribute. Yeah, we will see that in the here how it is being stored. And also what I have done here is in the second step is no, this is the second line. So this will sort the data. So let's say if the area is 100 square kilometer, 50, 20 and 10 square kilometer, and there are several other data set, then it will sort by highest number first. So if the area is 100 square kilometer, then it will be on the top, and in the second it will be lower than that area, and in that sequence. And I try to limit it to 20. So this is also just my guess, but in my case here, let's say if this was detected as a water body and this was also detected as a water body, then this looks like a third biggest water body here. So if I go up to 20 or 30 level, then I will start to notice that these will be small water bodies which might not be of my interest. So that's why I will just remove that. It is additional filter that I apply on the vector data set. Okay, so this might depend upon your area. If your area is very big, then you might want to change that number to, let's say, 100, 200, like that, to limit the amount of vector data set. Did I go? Yeah. So, but in my case, I just limit it to 20, and I display what is the result produced by this method. And if I see here, inside here, then column, sorry, in features, there will only be 20 data set each under each feature. The first feature has the property of area that I added by using this area function, right? So this area is calculated as 363 square kilometer, which is a very big area. But if you reach up to the very last point and see the properties, the area is 0.13 square kilometer. Now you start to notice that the area is reducing by a very big number after you go from below that. And yeah, so when you come up to 2020, there is only 6 smaller areas and you do not even have to filter it. So there are only 6 features here in last case. And the area is so small that it is 9 square kilometer for 2020, and the smallest area, water detected area, is 0.03 square kilometer, which is very small. Yeah. So if you run this step, you will be able to see for each year the feature, the vector data that you produce. So let me know up to this step whether you can run this or not, this script, where I say function to calculate area of geometry in square kilometer. We are almost at the end of this session. So because we already have the area, now we just need to plot the chart like we did yesterday. Yeah. This step will take more time. Yeah. The main issue is the main time taking factor, I think, is this area mainly, because for each so if there is 100 of area, then it has to sort it to make it has to sort it first and then limit it to only 20. So this sorting operation will take a long time. Yeah, it has to go through each and every data set for each and every year, so that's why it's taking time. Yeah, I think in my case it's done, or it will take some time. Yeah, because I have also not run this now. Okay, when this happens, let me explain the other code. So this process will complete and then we can move to the next one. Okay, so this in the earlier step, we just used to load a single data set into we just used to load a single data into our map, but now we have a time series map, right? So I just added the layer for each year in a loop. So instead of map.add layer for 1995, 2000, 2005 and so on, I can just run this script once, and for each year the information will be displayed on the map. After we run the earlier step, we can see this. So yeah, if you have any queries, then you can ask up to this point. I think it will take a few minutes to load this one. This part is for display. Yeah, this part will be easy to understand if we complete the audio step anyway. Yeah. So let's wait for a while. And after we complete this step, we'll move on to the next one where we just plot this data. So this is like three steps process. Yeah, maybe I'll explain this block of code here first. So when we move to the plot section, it will be easy to understand. Yeah, so first of all, I need to know the area of the water for each year, right? To plot this kind of data set. For 1985, what was the square kilometer of water, uh, area of the water for that year? So to plot this, so first I initialize this water area as an empty list, and then I take the keys, like the key was, as earlier also I discussed, the key is same as this list. Yeah, this is the list, because we want to iterate through this list, right, for each year. And yeah, and for item in keys, so it means first it will take for 1985, and then it will reduce column. So first it will take the item, and it will take reduce column. And what this reduce column does is it will take one column that you specify here. So in this case you are specifying the area. So we already calculated the area column, and I think one is already processed. Let's see for this feature. Yeah, it will take this area feature right here, and then try to get the sum. So as I mentioned, for 1985 there is 20 different lake, right? So we have to get the area of all 20 different lakes, not the first one, not the second one, but combine all of those areas. So here we do water mask for that individual year, and then we reduce the column by and the reducer operation is sum. If you remember, earlier we used the reducer operation median to do the kernel filter. Yeah, and then we do the sum based on the area property, and finally after the calculation is done, the final output will be saved in the sum attribute. Yeah, for each year. So we have to get only that sum information, and this get information will get info function will convert Earth Engine data type to normal Python data type, so that we can because to plot this, our data type has to be converted to a Python data type. So this number is Earth Engine data type. So this, even this water mask vector is Earth Engine feature. So whatever operation we do, it will be only Earth Engine type. So if we convert that data type to normal Python number in this format, then we can do the plotting thing. Yeah, and then after doing the sum of area for each individual year, we append that into this list, into the water area list. And now I have printed the data, print water areas after doing the calculation. You can see it was empty at first, and after we calculate and append, for 1985 it is 480 square kilometer and 793, and you see the highest water is in 95. Yeah, for the 1995 the water is highest, and it subsequently reduces after that up to 9 square kilometer at present. So this is the chart that is being plotted now using the matplotlib library. So in the x-axis we have time frame, and in the y-axis we have water area, like here. So the data for time frame is 1985 to 2025 at each 5-year period. So normally this range function will exclude the last year. That's why it is not showing 2025. But if you put 2030, then it will show up to 2025. So the usual concept is that the range function will start from 1985 and end at 1 year, one step before this 2025. Yeah. Let's see if it is calculated. So only 2 is done yet. So I think we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, at least 6 left now. Yeah, let me know if it is completed in your part. Completed. Okay, so if it is completed, you can run the immediate next step, and you can view all the, I mean, for every year how the water is changing. Yeah. In this step. Yeah, let's wait a few minutes until mine is done, and yeah, then we can visualize it and then print the chart. Done. Okay. Okay. Yeah, I think mine is half completed. So otherwise, if you can visualize this, then you can share your screen also. If anyone is, if you can visualize this step, or you could wait for another few minutes, and yeah, we can export the data set. So the code is very similar to what we did yesterday. Let's see. Take this one. Yeah, I think we exported for DEM. Yeah, yesterday. It's the same. Yeah, the same step as we did here. So ee.bash.export.image, and then instead of elevation, you have to pass in the water mask. Yeah, and the region and scale. I think you can use 30 for the scale. It's fine. And instead of DEM Afghanistan, you just replace it with water mask. And, you can export the raster by that. But for vector, I have to check it. Okay. Yeah, you can also do that in ArcGIS. If you export the raster, you can also convert that in ArcGIS. Okay, so that is the vector data, right? In the end, yeah, that's correct. So I check the documentation instead of ee.export. Yesterday we did ee.bash.export.image. You can use export.drive to drive. Sorry, export.table to drive, and then it will export the table. So the vector dataset is can be referred as table in yeah in Google Earth Engine. So here is the link to documentation that I used. Yeah, you can follow this step, and then I think you can explore. Yeah, actually The thing is, I did not look into the cause for sudden drop in water, but yeah, I only try to visualize it, but I don't know the background reason for the drop in water in that lake. You can check in the internet. You might know, was there any like just let me check for a moment. So yeah, the internet just says that the global warming was the main cause. For the team model said the global warming was the primary culprit in disappearance of this lake. Yeah. So maybe due to the warming of Earth. Okay, so this process is completed. Um, next next step is that. Oh, still running. So maybe Toast or you, Sophie, you can share your screen and run this one, so all of you can see. Yeah, sure, sure. I think we have to go 5 more minutes. Yeah, sure, sure. I think that would be good. Okay, can you share your screen? I'll make you co-host. Just a moment. Yeah, now I think you should be full share. Okay. Surface water.
You are seeing my sheet?
Yeah, I can see it. Yeah.
Oh.
Okay, can you go on the top? Yeah.
Where?
Yeah, so after you complete the previous step, so this one is the second, display the extracted vector water, right? So previously it was raster and we converted to vector, and we want to
Vector.
visualize this vector layer. So if you run this, can you go down a little bit, or maybe
Map. This
can
is
you
the
make
result
your,
for.
yeah, can you make your browser full screen, so the is will from the top right corner, or you can press F11 in your keyboard.
Full screen.
And in the top right corner of your browser, there's a small 3 dots, right, in the top little above that, above your photo. Yeah, there, full screen. In the right side of the zoom, there is the arrow down. Yeah, that one. Okay, so if you click on this setting icon there in the top, can you go a little bit up? Yeah, little up.
Little.
No, scroll a little bit up for this notebook. Yeah.
Where?
Yeah, scroll a little up. Yeah.
Yeah, pardon, like
Yeah,
sitting there.
it's okay. Yeah, go a little bit down. Yeah, here. Okay, it's fine. So you can see in the map, top right corner of the map, there is a small setting icon, right? Click there. Yeah, and go, yeah, there. So you can see this, all these layers are loaded. You can turn all of this off first. Yeah, double click there. Okay, so now all of them are off. So click on OpenStreetMap, yeah, and 1985 Landsat. So this is the image for 1985. Can you zoom out your image a little bit? Yeah, minus. Yeah. 3-4 times, yeah. Yeah, 1 or 2 times more. Okay, 1 or 2 times more, yeah. And yeah, now it's fine. Scroll a little bit in the frame. Okay, so if you see the water mask beyond that scene, there is water mask 1985. Yeah, click there. So you can see this is the water mask for 1985.
Okay.
So if you see in the 1990s, similarly you can see the satellite data. Yeah, you can cancel it here. 1990 and 1995. Similarly, you can visualize it and you can see the change annually.
1990.
Yeah. So this is the 1990
Okay.
image and water mask
Yes.
again.
Water mask.
Yeah. So this is the water mask detected, right? Vector
Okay.
data. Again, another one, 1995.
1995. This is the water mask.
This is the water extent. Yeah. So you can see the water is maximum in 1995, right?
Okay.
So let's see for 2000 again.
Mm.
So now the water is shrinking again.
Yeah, this is. Oh, 5 pencil.
2005. Yeah. And the water is almost completely disappeared after this. Yeah, this is how you can visualize it.
2015, 2000. Este دومره اقل شوی ده سره ډراپ شوی ده
شوی به دا اول ځل د زه ګورم نو دا به کتل غواړي ما هم دې لپاره ویل چې دا انولي که نه بیا به پرزنټیشن سره سړی چک کي خو دا به صحیح په دې به یو بل کار جوړ کړو یو وړوکی پیپر به په دې بل ولیکو انشاءالله
شاید دا بیخي لکه ختم دي 19 هغه ته وګوره 85 ته تر 20 ته صحیح ده نو
Okay, so after you visualizing this step, I think let's move on to the next one.
Okay. Next step then we have this one.
Yeah, can you run this?
I already run this one. They gave the 9.6.
So I wanted to, in this step, we just want to see what was the data inside inside the feature collection. So the first one is feature collection. In the top you can see we have water mask 2020, right?
2020.
In the code. So it means it will take all the water boundary for 2020. So it is a feature collection. So there is currently 6 items. So 6 water boundary has been detected in that time frame. And if you go a little bit down in the feature, I extracted I think only the first one to see what it looks like. So to study its properties, you can go to feature. Yeah, click on feature and then go to properties. Okay, there also you can see the area, right? But you can also directly see the properties like below. The same properties information is also available down. Yeah, 9.698. Yeah, so to understand what is inside your data, you can follow the above code.
Okay.
I mean, first there is a feature collection. I mean, there is 8 years of data, and you can just filter that according to your requirement. And this I think you already done, and I also explained this. We try to take the sum of all the water boundary detected for that particular year, and after doing the sum, we plot the data set. Yeah, because each year has at least at maximum of 20 different water boundaries, right? So we have to take the sum of all the water boundaries.
Okay.
Yeah. So the last step, if you run that, you can see this plot. So you can see the water was slowly increasing up to 1995, and it peaked out at that time frame, and then it declined rapidly. Yeah, I think also the problem was if you see the surrounding, the water is not recharging in that area, right? So that could also be reason why the lake suddenly disappeared. Okay, I think we are all done.
Okay, thank you.
Thank you.
Thank you, Helson, for today's session.
Yeah, I have one more thing to share. Can you see my screen?
Yes, we can see your screen.
Yeah, so in the end, there is one additional material, a notebook.
Okay.
You can visit this website. So in the presentation slide, I mentioned about single band based method, right? So this is just a simple demonstration of single band based thresholding. So I think now if you look at this code, it will be very easier to understand for you, because all of the thing we are again reusing again and again.
For single band.
Yeah, so for the single band, we just take the image, right? And this is the image. So the difference is previously we used the optical image, but this one is the SAR, radar based image. So the advantage is that whenever we want to monitor water boundary in the flooding scenario, there is always cloud cover, presence of cloud. So in that case, it becomes really difficult to measure by using the optical imagery, and hence we have to rely on this SAR imagery for that purpose. And so the
Yeah,
main
this
concept is here, like I used a vv.lt16 rename water. So this is the main logic of the program. Everything else, as I did earlier, we do some filtering and to minimize noise and all those things. But in this case, we just use a single band called VV band. So in SAR imagery, there is VV and VS band. So we take one and then we apply the threshold. If the value is below 16, you identify it as water. And if the value is greater than 16, it is not water. So because the water will completely absorb the signal that is passed by the radar image, by the radar satellites. So using that concept, we did the thresholding, but you can see that the prediction is okay, but it is not very accurate. So it is so whenever we are moving to the edge, the detection is not good. Even the edge is detected as water, which is false. And if you see here, even the area which is not like a water will also be detected as water. So this is the main issue if you rely heavily on a single band thresholding. So that's why we are doing the combination of multiple indices like NDVI, NDWI, and EVI. So those combination will produce better result. So if I have to give a reason for this, then SAR image will be more affected by cloud and also the surface structure. So if there is some shadow, if there is a small hill and the hill will cast shadow on the other side, then that area will be dark in radar image, and hence this area will also be detected as water, which is a false information. This area does not have water in it. So if you rely heavily on a single band thresholding, then this kind of problem can occur. So yeah, this kind of approach is more improved over the approach that I mentioned here. So I think that's all. And if you have any questions, please feel free to ask. Otherwise, we can end the session for today.
Okay, thank you. No question from my side.
Okay, thank you. A question? Okay. Thank you, everyone.